Thanks for coming. Sorry about the technical difficulties. So I want to talk about a joint work in progress with Hannah Markwig and Sam Payne. I think Sam was here. Maybe he's not here anymore. Where we tried to give a tropical approach to so-called enriched counts of bitangents to smooth quartics. So the kind of classical approach was done by Larson and Vogt, and I'll start by giving a rundown of, well, plane quartics, bitangents, and also tropical geometry. So I'll fix some conventions. We'll work over a field that's not of characteristic 2. That'll be important pretty much through my whole talk. And I'll fix Q will be a quartic polynomial, homogeneous in 3 variables. And C will denote the quartic curve that this defines, so the 0 locus of this quartic polynomial. And I'll always want it to be non-singular for my talk. And I'll say a line is bitangent to C, so this is not a surprise, if the intersection of the line with the curve C consists of either 2 points, each of multiplicity 2, or we could also maybe have 1 point of multiplicity 4. And it's a very classical result that goes back to Plucher and Jacobi, that if the field is algebraically closed, so say the complex numbers, then every non-singular quartic curve has exactly 28 bitangents. So a non-singular quartic curve, the curve itself, if we're over C, would be a genus 3 Riemann surface. So this is kind of a cartoon picture of a CP1 a line being bitangent to the curve. And it could seem like these are sort of not very, well, sort of extrinsic things to look at or to count the bitangents, because they have to do with, well, the curve being in the plane and then lines touching it in a certain way. But it turns out that these 28 bitangents are very intrinsic. So they correspond to odd theta characteristics. And it was actually shown by Caparassa and Cernesi that if you know just the 28 lines, you can even recover your bitangent lines. You can recover your quartic curve. So these are very intrinsic objects to look at. And the number 28 is invariant over an algebraically closed field. If we switch to say a non-algebraically closed field, then the number of bitangents depends on the equation defining the curve. And also a very classical result of Zeuthen from, well, just slightly after Plucher and Jacobi, determines for, well, all the different topological isotopy types of quartic curves in the plane, the number of real bitangents. So in the case, so there's a bound given by Harnack on the number of connected components that a real non-singular real algebraic plane curve can have. It's going to be genus plus 1. So the genus was supposed to be 3 here. And so we have a maximum of 4 components. And in that case, all the bitangents are actually real. So if we have these 4 connected components and we have 28 real bitangents, the next case where we have 3 connected components, there's exactly 16 real bitangents. And the next case of 2 connected components that are sort of separated from each other, there are 8. Now in the next case, there are also 2 connected components, but notice that the way that these connected components are embedded in the plane are different. Here they're nested. This is a so-called hyperbolic curve. There are 4 bitangents and then 4. And lastly, there's another topological type of real curve, which is just the empty set. So you can have no real solutions to your equation. So this is not a picture of a curve, that's the empty set. And there, even though we have no real points, there are still real bitangents. So by a real bitangent, I mean a real line that is tangent to the curve in 2 points, but those 2 points might not be real points. So here we have lines that are bitangent at complex conjugated points, and we have exactly 4 of them. So this classification was done by Zeuthen over the real numbers, and so these are sort of the total classification of the real types of quartic curves, and the number of bitangents only depends on that topological type, real bitangents. So what I want to talk about is some tropical geometry and a tropical approach to these kinds of problems. So if we switch to the field, well, not being a field, but to being the tropical semi-field, so that is this thing denoted by a bold face T, then it's a result of Baker, Len, Morrison, Pfluger, and Wren from 2015, that every non-singular tropical quartic plane curve has 7 bitangency, so classes. So it's not 28, it's not these numbers here, it's this odd number 7, and so the word classes. So I want to explain what this means, basically via examples. So what is a tropical quartic curve? Here's an example of one. So these tropical curves will be piecewise linear kind of graphs embedded into the plane. They can be defined with tropical polynomials. We'll see how they arise from honest curves in a bit, but I want to start with some examples. And every curve will have a kind of so-called dual subdivision. This will come up also later in my talk. And for the curve to be non-singular, the dual subdivision is going to have, so these tiny pieces that are somehow, there's a correspondence here. The pieces in this dual subdivision will have to have sort of Euclidean area 1/2. So this is the smallest lattice triangle we can come up with. So a tropical line will be a special kind of piecewise linear graph in the plane, and it'll look exactly like this tripod thing. And the vertex can be placed kind of anywhere, so any coordinate r comma s in R2. Then we can define intersection multiplicities. I'll just do it kind of generically. So if I have a red curve crossing a black curve in some point in the interior of an edge, then the intersection multiplicity of these two tropical curves is just going to be the determinant of the direction. So when I say directions, there'll be a smallest integer direction in the direction of each of these edges, and I just take the determinant. It's not so important the precise definitions, but with these intersection multiplicity definitions and tropical curves actually satisfy a version of Buzot's theorem. Yeah, so just like we defined bitangents via intersection points and multiplicities, we can say that a tropical line, this lambda thing, it will be bitangent if when we intersect the curve, this gamma curve with the line, we have either 2 connected components and the intersection multiplicities in each connected component total to 2, or we have 1 connected component and the total intersection multiplicities total to 4. So I'm just going to describe this with a picture. So I'll draw a line here. Oops. Something like this. Here you can compute the intersection multiplicity, as I told you, down here, and you get an intersection multiplicity of 2. So that kind of looks like a tangency point. Here it's slightly trickier. So what I mean is, to get the intersection multiplicity, you can sort of slide the curve off a little bit, the line off a little bit. You compute the intersection multiplicities in the situation that I've described, and you get a 1 and a 1. And when you slide back, you take the total sum of the points and their multiplicities when they converge to this intersection component. So here I would also have another component in the intersection of the line and the curve with the total multiplicity of 2. So this would be a so-called tropical bitangent. Now, notice though that if I move my line ever so slightly, the same calculation holds. And if I put a tropical line sort of anywhere along with the vertex, anywhere along this segment, I would get another bitangent. So it looks like we have an infinite number of tropical bitangents with this definition. it doesn't seem so great from an enumerative geometry point of view. So here's where the bitangent classes come in. Keeping the same example of the quartic curve, anywhere, if you put the vertex of a tropical line at any one of these red points, you'll have what, by the previous slide's definition, a tropical bitangent. And notice then that there are all of these red points, they have in these different connected components, and there are exactly 7 of them. Okay, so these are the 7 bitangency classes for this type of, for this particular curve. And actually, Cueto and Markwig classified the types of bitangent class shapes. So there are, each curve has 7 bitangency classes, but there are, I guess, 39 combinatorial possibilities for what these types of bitangent classes look like. So there is a connection between tropical curves and classical curves. And it comes via the tropicalization map. So I'll stick with a field little k not being of characteristic 2. And for this talk, I'll use the field of Pizot series over the field little k. So these will be like formal power series in a variable t, except we allow fractional exponents in t, with the requirement that when I take one series, all of the fractional exponents have to be written over a common denominator. And so when I have an element of one of these series, the valuation map will take a series to the exponent of the so-called leading term. There's a question in the chat. That's a good question. Do I consider lines with equations max x comma y? For my setup, if I'm looking at bitangents and I have a curve with a dual subdivision, kind of the max Newton polygon for a quartic curve, these will never be the bitangents. So you're right that there are different types of tropical lines that one should normally consider, but they will never be bitangents to the curves I'm considering, so I can just ignore them. Does that answer your question, Vilos?
Yes, thank you.
Okay. Okay, so yeah, so we have the valuation map, which is the exponent of the leading term. And I'll also want to later bring in, so this is not necessarily for tropical, what we strictly think of as tropical geometry, but the initials of a series A, this will be the coefficient then of the leading term. So this lives in the field little k, which is little field, this little k is the residue field. So then when we have a homogeneous polynomial, so like say our polynomial q that I started with coefficients in this field of Pizot series, the tropicalization for the purposes of my talk, this is a rather simplification, will just be, I can look at, well, first take the non-zero, the points in C with non-zero coordinates. And I'll look at the coordinate-wise valuation of the points in C. And this will give me something that, technically speaking, lives in the rationals squared. We can take its topological closure and have something in the Euclidean plane. General, we should put some weights and extra data on the tropicalization, but for purposes of today, you can just think that the tropicalization will be of a curve defined over the field of Pizot series will just be this set. And the condition that the tropicalization be non-singular means that this is all you need, basically. So I can make some simplifications. One thing that's kind of then obvious, since this tropicalization map only looks at the valuation, it completely forgets, well, completely forgets all higher order terms of your series, but it also completely forgets the initials. So the coefficients of even the leading terms. So just one more remark that, or two more remarks that, well, if the field little k, the residue field is algebraic. This is algebraically closed, then our field of Puiseux series is algebraically closed. So the first statement about the number of bitangents, if I work over the field of Puiseux series with complex coefficients, for example, should always have then 28 bitangents. And the second remark is just for what we do, we can use more general valued fields, but we need them to be Henselian, 2 divisible. So that rules out the straight up p-adics. We would need to make some modification because the value group of the p-adics is just z, so it's not, can't divide by 2 in the integers. And the valuation must admit a section. Okay, so using this tropicalization map, I can go from curves defined over the Puiseux series over some field and get some of these tropical pictures of these tropical curves. Now, then you could also take the bitangents to your curve and see to your original curve C defined over the honest Puiseux series field and tropicalize those and see what those lines go to. So they will be sent to tropical lines. And they will be sent to tropical lines, which would have to be bitangent to our curve. But the point is that not all tropical bitangents will lift to bitangents of our curve over the field. Remember, we saw that we have, well, infinitely many tropical bitangents. Any red point here, I can put the vertex of a line and it would be bitangent, but I only have 28 bitangents to the curve defined over the Puiseux series that I started with. So here's where the definition of lifting comes in. So we say that a lift over the field K of a tropical bitangent lambda is a bitangent L, so an honest line defined over the field K to the honest curve C defined over the field K, such that its tropicalization is our line. And for example, in this particular case here, such a line, such a tropical bitangent with its intersection point in the middle of this green segment does not lift. The only ones which do lift are the two which intersect here at vertices of the tropical curve. And moreover, a tropical bitangent may lift to more than one honest bitangent. And here, this is what these numbers 2 and 2 are signifying. So what this means is that there exists exactly 2 honest lines L when we're in the case of an algebraically closed field, which when you tropicalize them, which are bitangent, which when you tropicalize them land on this line, and similarly here on this line. So this is summed up actually for every bitangent class by a theorem of Len and Markwig, which says that a tropical bitangent class, of which there are always 7, right, by the theorem of Baker and co-authors, a tropical bitangent class to a non-singular tropical quartic lifts to exactly 4 bitangents when your field of Puiseux series is algebraically closed. So this is nice because, right, 28 is equal to 7 times 4. Right? So that means that we can account for all of the 28 bitangents over an algebraically closed field. They come packaged in groups of 4 and they land in each of those groups of 4 land in a bitangent class of the tropical curve. So here, I won't do it for all of them, but we can write multiplicities on the liftable bitangents. These are the ones that have the dots on them. So if I put a line at a vertex with its vertex on one of these dots. It'll be a liftable bitangent, and the number here signifies how many lifts there are. So actually this 28 equals 7 times 4. It's some nice numerology, but there was an explanation for it given by Pacini and Testa. So they explain this multiplicity 4 by looking at exactly at the characteristic which I'm avoiding. But when the characteristic of the field is actually equal to 2, then we only have these 7 bitangents, and we can still study them tropically. So they look at an explanation of these tropical multiplicities coming by fields of characteristic, which typically we would then avoid because the numbers change. Then, well, more recently, over the case of non-algebraically closed fields. So first over the real numbers by Cueto and Markwig, and part of our work with Hannah and Sam was to look at what happens to these bitangent classes when you're not over an algebraically closed field. And our first theorem is that when you have a tropical bitangent class, you can actually determine that there are either all 4 of those bitangents that lift. So either you get exactly 4 bitangents that lift over a non-algebraically closed field, or none of them. And it's whether or not these lifts is determined by, so the information that we want to then keep track of are the initials of these coefficients. So these are the coefficients of Q. And not just the initials, but we can actually forget some information of the initials and just need to know the initials, the class of the initials, modulo squares in the field. So in the real numbers, the non-zero real numbers modulo the squares of non-zero real numbers is just plus or minus. So you just need to know the signs of the coefficients of all of the signs of all of the coefficients of the defining polynomial. And well, to help us determine these lifting from the sign data, we introduce a notion of arithmetic twisting. So I want to show a little bit about what this arithmetic twisting looks like, and also then relate it back to the real case to explain where the name comes from. So just to remind the conventions, we have Q, homogeneous polynomial. I want to index it actually just for some convenience. Think of dehomogenizing so that the index here in this exponent will be in Z2. Okay, so think of it as a polynomial in X and Y that can be homogenized, and S is just the integer exponents of X and Y. So C is still our curve, and our coefficients are in this field of Puiseux series. The initials then live in the field little k. So the property of twisting will come up for edges, and this is one thing that helps us determine whether the bitangents will lift over a non-algebraically closed field or not. So why we look at edges? Well, we saw in one case of a bitangent, let me just pretend this is a piece of a curve gamma. So this is not a whole quartic curve, but this is just one little piece. And maybe some line lambda. We saw that this was a component. This is a component that has an intersection multiplicity 2. So this is a good candidate for a tangency. And we can determine whether this tangency is, whether this, a bitangent with this one connected component, this piece, would lift over K by looking at the so-called twisting property of just the curve itself along the edge E. So what is this twisting? The edge E of the curve will be dual to something in the dual subdivision. This edge here, so dual things are perpendicular. And in the dual subdivision, we'll have some lattice points that will correspond to monomials of this defining equation Q. And these monomials are indexed by, well, the coordinates of these points are lattice points. And so here's a definition of twisting over R that we adapt to the arithmetic setting over a general field little k. So it's totally technical, but it'll have a geometric interpretation in a second. That the bounded edge is twisted over k if this product, so these are the initials, if this product is not a square in k. So these deltas are just 0 or 1, depending on whether these 2 points have equal coordinates mod 2. Okay, so it's just some product of the initials. And since we're asking about this being a square, again, it suffices to consider all of these, even the initials and this whole product, in the non-zero elements of the field modulo squares. And then there's a more general definition of relative twist, and this could be when we have, say, a line like this intersecting an edge of the curve, and this would also give us a candidate for a tangency. So then we have a little bit more complicated situation where we have to take the initials of the equation of the line and the initials, so I call these B's, and the initials of the equation of the curve. And similar thing is just something is relatively twisted if some product now actually is a square in K. So it's slightly opposite. Here it's not a square and here it is a square. But the point that I just want to make is that all of this comes down to, well, not only just looking at the initials of the coefficients, so I don't need to remember these entire series, but just looking at the initials and also just looking at the initials mod squares. So when you're in the field R, for example, initials mod square again is just plus or minus. Similarly, if you're in a finite field, initials, the non-zero elements mod squares is also just plus or minus. This is the Legendre symbol. So one of our theorems that helps us determine the lifting over fields or not of these bitangents, so whether 0 or 4 of the bitangency classes, whether a bitangency class gives us 0 or 4 lifts over a non-algebraically closed field, especially in the case of these so-called two-edge bitangencies. So that's when, if you have a line intersecting, a tropical line intersecting your curve, and each of the two connected components of multiplicity 2 happen to be segments. So we can completely determine whether it lifts over a non-algebraically closed field by the twisting and relative twisting. So a single tangent will be defined over the little field K. Sorry, there should be a bold here. Will be defined over K if E is not twisted over little k. And similarly over in the relatively twisted case. So it's strange to think of, well, why does this word twisting comes up? And it happens to do with, well, the topological situation over, if we look at the field R. So what's in the name twisting? If we take little k to be R and we look at the field of Puiseux series with real coefficients and take some curve C, then we can look at, well, the so-called amoeba of the curve instead of taking valuation coordinate wise, we can take the logarithm coordinate wise, but when we, sorry, this should be, if we assume that our coefficient, we have a small enough t so that our coefficients are locally convergent, then we can have actually an honest curve defined over the real numbers. And we can take the coordinate-wise log of the absolute values of the, sorry, we can take the coordinate-wise log absolute values of the points that are in CT. This is so-called amoeba of Galfond, Kapranov, and Zelevinsky. And if the tropicalization of this is non-singular, like the curves that we're considering, then what happens is that for large enough t, the so-called amoeba around an edge can only do one of two things. So the amoeba will kind of give us a band around the tropical curve. And at bounded edges of the tropical curve, the amoeba can kind of either lay flat, like a flat band, or you can have a so-called twist in it. So these would be like inflection points of the real part of the amoeba. And so this is where the twisting, non-twisted comes up. So non-twisted if the amoeba lays flat, and twisted if you actually have like a Mobius band twist. And over the real numbers, this is a kind of complicated way of saying that the amoeba twists. So all you need to know whether it twists or not are the signs of the coefficients of these monomials. So the signs would be exactly the class here. And well, kind of a precursor to that, this twisting in amoebas is, well, a method introduced by Viro, who's here, called Viro's patchworking, which he called patchworking. And this is this is a method that from data of, well, a tropical curve and some fixing initial data of some initial coefficients allows you to cook up real algebraic curves with prescribed topology. So I won't give a full comprehensive introduction to what this method is, but I want to say some speculative things about what I hope these arithmetic twisting does. So what Viro's patchworking allows you to do is fix some input. The input is a regular subdivision of a Newton polygon. So say this Newton polygon here. This is a regular subdivision. It means that there are some function on the lattice points defining this subdivision, and some sign data. So think the sign data is exactly a class here in the non-zero reals mod non-zero squares. And via procedure, what it outputs is some curve, possibly piecewise linear, some curve in the real projective plane. And Viro's theorem says that, paraphrase, that there exists a real algebraic curve C defined over R such that RP2C, the pairs RP2 and the real part of C is actually isotopic to this thing that you construct from just this purely combinatorial data. But it's much more than just a purely existing statement. It is rather constructive. And there's a link with tropical geometry in a sense. If you fold this picture back up, what you can get is the amoeba wrapping around a tropical curve. And so you can almost in a sense go back from, if you know, specify some twisting data, you can go back and forth between Viro's original formulation of patchworking and this twisting formulation. And so another situation where our field modulo square, or non-zero field elements modulo squares are rather simple is, for example, when k is finite. So when k is finite, we also have the fact that the non-zero elements modulo squares are just pluses or minuses. So this is just given by the Legendre symbols. So one proposition could be, instead of remembering the initial terms, try to just remember the Legendre symbols of all of the initials of your coefficients. And the question is, what else then could be determined by this data? So you have some curve defined over a field of Puiseux series, say possibly with little k now being a finite field. What can you remember if you remember the initials of the coefficients, but also what could you remember if you just remember the initials mod squares? And for example, in our lifting question for bitangents, one thing that's kind of nice that comes out of this is that it's the following corollary from, well, this theorem and theorems that generalize not just to two-edge bitangents, but is that if we have, say, the size of k being a prime, which is congruent to 3 mod 4. So in this case, this means that -1 is not a square. Just like in the real numbers, -1 is not a square. Then the lifting of a bitangent class over the field of Puiseux's series over that field is kind of quote unquote equivalent to lifting over the reals. So what does it mean equivalent? It means that if I have a curve defined here over this field, and I take the exact same, a curve with the exact same initials modulo squared defined over the reals, and the same exponents of leading terms, then I can determine the lifting over this Puiseux series with finite residue field in the same way that I would determine them over R, which is very kind of more topological. And a question, I guess, yeah, what else besides just lifting of bitangents can be determined by these initials modulo squared? Kind of a arithmetic, I don't want to say arithmetic patchworking because it's not topological, but it's sort of trying to stream down the amount of data that's recovered in an analogous way to Viro's powerful method. All right, so Alicia, do I get the 10 minutes or should I?
Yes, of course.
Yep.
Yes,
Yeah, okay.
have 10 minutes.
Like 10, should I end at 11 or should I? Yeah, okay. So this lifting over non-algebraically closed fields of the bitangents was what we first needed to do in order to consider this enriched, a tropical approach to this enriched counting of the bitangents to quartic curves that was initiated by Larson and Vaught. So remember that over the real number, I'm going to get into this enriched counting, but again, via the real perspective, because that is one of the interesting things of these enriched counts that they propose. So if we go back to k being the real numbers, remember that Zoythan said that, well, there are these we knew that there are these different topological types, but he classified how many real bitangents there are in each case. And what Larson and Vaught come up with via this enriched counting, eventually, I haven't said what it is yet, is they determine that there's actually an invariant if you make a signed count of these bitangents. So there are 28 bitangents here, and we want to count them with plus or minus signs depending on a certain topological property. And what that property is, well, if you look at your bitangent and you look in an affine chart, okay, it's very important that you look in an affine chart, then either the two branches of the curve are on the same side of the line in that affine chart, or the branches are on opposite sides of the line in that affine chart. And then they assign -1 to these types of bitangents and a +1 to these types of bitangents. Add them all up. I should also say you have a +1 to these types of bitangents, which have their tangency points in complex conjugated things, right? This recipe wouldn't work for you. So you give a +1 to those types of bitangents as well. And what Larson and Vaught managed to show is that, well, as long as your affine chart, okay, the line that you choose to define your affine chart, so your line at infinity, does not touch the curve, then the sign count is always 4. And the way that they come up with this invariant is via, well, these enriched counts to bitangents. And in this case, when your affine chart, when your curve lives entirely in the affine chart, so it doesn't touch the line at infinity, they managed to show that there's a bundle, which they consider, which is relatively orientable, and that just immediately gives invariance. But what they do as well is define just so-called Q types of bitangents. So this enriched counting is, well, it's a general proposal of counting kind of beyond using numbers, of enumerative, beyond enumerative invariance with numbers. And it's to count things with quadratic forms. So this comes from A1 homotopy theory, and the places to look for background information are Cass and Whickle-Green's papers, Mark Levine, and everything I learned about this was from Sabrina Pauly's thesis. She was a PhD student in Oslo. So yeah, the idea is to assign to then the things that you're counting in your enumerative problem, not a number, but a quadratic form. So quadratic forms as in elements of the Grothendieck-Witt group. So what are the generators of this Grothendieck-Witt ring? So it's generated by every non-zero element of your field K. You get one quadratic form of rank 1 by just taking the form that pairs x and y together to give A times xy. Okay. Now the relations that we want to consider in this group, so you should think that these relations are kind of just, I mean, equivalents of quadratic forms in a sense. So if you multiply A by some square number, then, I mean, you can rescale change your coordinates and you get the same quadratic form. So this is kind of also why this importance of only caring about non-zero elements up to squares also fits, that we did with the twisting, also fits with this Grothendieck-Witt group. And then there's this one more relation about sums of quadratic forms. So we mod out, but we take the group generated by formal thing generated by these, and we mod out by these two relations. And there's one special element, which is the hyperbolic form. So it actually turns out that using just these two relations for any non-zero A, this rank 2 form is always equivalent to, say, the form with 1 plus -1 each in brackets. And the other indication that tropical geometry could be helpful with these computing of these enriched invariants is the following theorem. So K here is, again, this bold K is the field of Puiseux series over the little field K. And the theorem that we prove is that there's an isomorphism between the Grothendieck-Witt group over the field of Puiseux series and the Grothendieck-Witt group over the little field K. And this is simply given by the rank 1 form with the series A in brackets gets sent to the initial of the rank 1 form. So what Larson and Vaught define in the case of bitangents is they assign to each bitangent to a curve. So the curve is defined over the field K. The bitangents are possibly defined over some extension. And what they do is assign to it a quadratic form to a bitangent based on this formula. So take the directional derivative at one tangent, evaluate at one tangency point times the one associated at the other tangency point, put that in brackets, and that's a quadratic form. Now it's a quadratic form that lives in the growth and liquid group of some field extension, and we might want to only consider quadratic forms over the growth and liquid group with the field of definition of our curve C. But that's fine because we have the trace map. Okay, so our main theorem is that if we have C being a non-singular tropical curve, the Q-type of all of the bitangents, so over the algebraic closure, the field of definition of C will have 28 bitangents, right? And all of these bitangents, no matter where they're, the field of definition that they are defined over, their Q-types can be computed from this trop C and these initials of the coefficients of the defining polynomial. And in fact, the initials mod squares. So what's important here is that, so in the Larson-Vought setup, you're free to choose your line at infinity wherever you like. If you want this invariant, you should choose your line at infinity to not touch the curve. But to define this Q-type, you can choose your line at infinity wherever, you just don't get an invariant, unfortunately. In our tropical setup, we're really restricted. The line at infinity can only be the so-called line at infinity, as we think of in the usual homogeneous coordinates. So z equals 0. I just want to give one small example. So let's look at, if we look at this. Bitangent class that just consists of one line. So this is supposed to have 4 lifts over it. Turns out those 4 lifts, depending on the twisting of these edges, these 4 lifts could either be defined over the original field of definition of C. So it could be defined over, oops, sorry, this should be a boldface K. Or they might be defined over an extension of degree 2, both of them, or they might be defined over this extension of degree 4. So I could have a problem where, this is twisted and this is twisted, in which case I would need to maybe extend 2 times. But in either one of these 3 possibilities, the total Q-type of the contribution of all of the lifts ends up being 2 times this hyperbolic form. So this is a rank 4 hyperbolic form. And actually the rank of the form will always give us an invariant count of 28 bitangents. Okay, so we can compute these Q-types. However, we don't recover this invariant of theirs because our curve will always intersect the line at infinity. This is just kind of by design of the line of infinity that we are forced to choose in our tropical picture. But there was an interesting conjecture, it's still open, of Larson and Vought. And that's what happens with these Q-types when you don't insist that the line at infinity be disjoint from your curve. So this is a picture taken straight out of their paper. And what they conjecture is that, so now you let your line at infinity kind of vary and maybe it touches your curve. So here's these lines here are different choices of lines at infinity. And then the color coding in their picture tells you then the difference between the number of real bitangents with Q-type, the quadratic form with 1 in brackets, and minus the number of real bitangents with the quadratic form of -1 in brackets. And these supposedly lie in the set 0, 2, 4, 6, or 8. And well, so it would have been nice if we would have actually, well, if the conjecture is not true, to have been able to find a counterexample tropically, but because, well, we don't manage to, of course, prove the counterexample or prove the conjecture tropically because we don't have the flexibility and freedom of choosing all curves and all lines at infinity. But what we do show is something that if we look kind of just only at these curves that have non-singular tropicalizations and our line at infinity that we're forced to choose, then these numbers always lie in 0, 2, or 4. Yeah, so one thing that we would maybe be nice to be able to do is if this tropical approach would to lead to new invariants. So as we said, this difference in general is not an invariant. It's always 4 if this line is disjoint. The line at infinity is disjoint. So far, I mean, there's so many cases to consider and so much kind of data that over other fields, like fields different from R, we haven't been able to come up with any new invariants from the tropical perspective. But I hope that this twisting and non-twisting over fields other than R might be useful for other problems. And also that the kind of tropical approach to these enriched invariants can be applied in other places as well. So I think I'll stop there to sort of end on time.
Thank you. Very nice lecture. We have any questions for Chris? In fact, I have one. So do you envision to use these for what beyond Portix?
So I did have this slide prepared, but I skipped it. So there are many other problems where this enriched count has actually really concretely been carried out. So this kind of, I guess, machine or theory of these enriched counts is very, very, very powerful. But actually to kind of, so what Larson and Vaught do here with this definition is give a rather than using the Euler numbers of bundles and things like this, they give a very kind of concrete geometric description of what the kind of so-called Q-type contribution for bitangent should be. Another place where this has been done is for cubic surfaces. But here you actually get an invariant. So the case with the Q-type of Larson and Vaught is only an invariant sometimes when your line at infinity does not touch the curve. One could say, well, what about these other places where this enriched count has been carried out? Is it worthwhile to also try a tropical approach? I think one should be careful because certainly if it's an invariant, it just takes one surface with one computation to do it. But for example, in the enriched count of lines on a cubic surface, so there are 27 lines on a cubic surface over an algebraically closed field. The enriched count looks like this. So it's a rank 27 quadratic form. The signature of that form is 3. So this is the known real invariant, known prior to all this enriched counting. But to do this tropically, I think is maybe I would advise against it. I mean, it's well known that there are, well, to tropical people anyway, that there exist cubic surfaces that have infinitely many lines. So again, you don't know which ones to count. It's kind of like our bitangency, tropical bitangents are infinitely many, but we had to find the right lifts. This is still not really well understood. And also, if you look just over the reals, then there's a result of Bertrand that tells us what the Euler characteristic of a real surface, cubic surface near the tropical limit is, that it would have this signature. So this is only one of all the possible types of possible topological types of cubic surfaces. And so it's not, and all the lines on this are actually real. They're all defined over the real numbers. And in terms of this lifting question, which I presented as a pre-question to the enriched counts, there are very good reasons to believe that if you have a non-singular tropical surface that came from something defined over a non-algebraically closed field, then actually all 27 lines are still rational. So I can say more of that off camera, maybe.
There's a question in the chat. Can you read it?
Yeah, though I think one can say that so this is in the study of Vigeland and then updated by Panizut and Vigeland together recently. So sorry, maybe I should say what the question is. Is it known whether tropical lines on tropical cubic surfaces fall into finite number of line classes? Yeah, but I think the problem is that still the number of line classes can be more than 27.
Mm. What, Oleg?
Yeah, may I ask, in patchworking, what was really the upgrade with regard to tropical? The quadrants are considered separately. You can see the distribution between these 4 quadrants. And here, this distinction doesn't show up. What does it mean? Is it possible to get back to that? Are these bitangent lines somehow sensitive to tangency points, or, well, I don't know. I have no conjecture.
Do you mean in the real case, or do you mean with this arithmetic?
In the real case, this is a distribution of everything, of the whole curve, division into this 4 parts which are quadrants. And here it doesn't look like that.
I'm not sure I understand the question. So with the, I mean, with the patchworking, right? We completely determined the
patchworking is really sort of version of tropical with science. So it's tropical over real.
Yeah. Yeah, and then with that you can completely determine the topological type of the curve, of the quartic curve. And I mean, okay, by this result of Zoeth, and then you know exactly how many bitangents you have, but you can actually find them once you've done this unfolding. That's basically also what we show. We kind of yeah.
Okay,
but I mean, I think part of the interest of what, I mean, I guess one could say that that's what Cueto and Markwig show. I think what we've tried to do is then do this over other fields that are not algebraically closed. And there is some kind of analogy with patchwork, at least in this setup, when we have kind of Legendre symbols that we can.
That's very interesting. Yeah. And
I mean,
in the case of, sorry.
No, I mean, I think it's very nice here. It's kind of cute, but I hope that it's very interesting for other problems. That's kind of my hope.
Well, for tropical curve over reals, we can consider, say, tangency happening in the first quadrant and in the third quadrant. And if there is a bitangent line which goes from this quadrant to that, it is interesting if, first of all, if it is count at all. Second, how it is count. So tropical over real, there are also coordinate lines, not only line at infinity, but also 2 usual coordinate lines, and the points of tangency are distributed over 4 quadrants. And
thank you. That's a very good suggestion. That might be something to look at for what we were saying of new invariants that might be found tropically. That's I don't know if anything could be invariant, but it's an interesting question to ask. Like, can you have both your bitangencies, both your tangents?
Through your examples and to understand how it is happening on the real plane with respect to lines. And another thing is that these lines on cubic surfaces, they are distinguished over complex numbers either, and it happens due to pin structure, P- structure, if I remember correctly, on the surface. So is there any way to translate this pin structure to tropical world?
I've thought about this a little bit, but not on this tropical hypersurface model. There's this kind of better, well, I think better models for degree 3 Del Pezzo, so not a cubic hypersurface, but another embedding of a degree 3 Del Pezzos where you see the lines more clearly. And there I've thought a little bit about exactly the pin structures, but I still don't have a definite answer. Some lines seem to have a completely determined type that you can't change just based on the type of graph that they give you. And other lines can kind of shape shift. So yeah, I don't know. It's interesting.
So in terms, well, these two problems are closely related because you can pass from cubic surface to quartic curve and vice versa. So everything that you have done should be translatable. Should have counterpart over there. And this, for me, even in classical situation, is still a miracle. How can we understand this pin minus structure in terms of curves without getting up to the cubic surface? Quite an interesting question. Well,
good point.
Many
Thank you. Yeah.
Thank you.
Mm-hmm.
Wonderful.
Thanks.
Great comments for a great talk. Do you have any other question? Otherwise, we thank you again for this very, very nice talk.
Thanks.
Thank you. See you soon. Take care.
Bye. Thank you.
Bye.